Welcome back everyone. In this video we will learn about telescopes and how they impact astronomy. So the primary purpose of a telescope is to collect more light. As you know, our own eye lenses can only collect a certain amount of light, and for telescopes we magnify that effect so we can see things farther away. And a typical large telescope is approximately 6 meters in diameter. And for a dilated eye pupil, if you see one of those optometrists, they give you an eye drop, they dilate your pupil so your pupil becomes larger during a certain time period, and that gets up to 6 millimeters. In other words, this is the maximum length that pupil can reach. And for these, we can actually find the area by using the equation area equals pi r squared. And since pi is a constant, we don't need to care about that. We can just put 6 times 10 to the negative 3 meters on the bottom and 6 meters on the top. Now, how many times fainter can the telescope see compared to the eye? Well, we can figure this out by doing the diameter of the eye over the diameter of the telescope. And we can do that by doing d2 over d1 squared. And d2, the diameter of the telescope, is actually 6 meters. So 6 meters over 6 times 10 to the negative third meters is equivalent to 1,000 squared, and that's 10 to the 6th power. And 10 to the 6th power is approximately 1,000,000 times. So the telescope can actually see things farther, actually 1,000,000 times fainter than the eye, and that's an interesting fact for all you astronomers. So what is the purpose of telescopes besides having the ability to collect more light? Well, a telescope also provides greater clarity. So let's just list this down. Purpose of telescopes. Greater clarity is the same thing as angular resolution. And from angular resolution, we can derive this equation. Theta equals to lambda over the diameter. And the lambda is the wavelength of the light that is being observed, and the diameter is diameter of the telescope. When we figure out theta, we want theta to be as small as possible. So a small theta is equivalent to greater clarity. And that just means that the images are more crisp and it's easier to identify. But some problems that we need to address are turbulence in the atmosphere. And that is due to the air molecules, which blurs the image at optical wavelengths. And that's one thing that we will address. I want you to know an important fact, and that is all the light rays that are reaching Earth are essentially parallel. The sun and planets and stars are very far away from us, and so the rays only diverge slightly, and they basically reach us. Pretend this is a sun or other star, I guess, and this is Earth. They don't diverge a lot, and they're parallel when it reaches us. So when were telescopes first used? Well, it was used by a man named Galileo Galilei in 1609. So the first telescope was used in 1609. When this man, Galileo Galilei, he observed the universe with a refracting telescope. And the refracting telescope is that light will be bent by the lens and it will be brought to a focus. So let's draw a diagram. Pretend this is the lens that we have, and light is coming in towards here. So as light comes in towards here, it gets bent, as this is what the lens does. And once it gets bent, it reaches a focal point over here. This focal point helps astronomers, astrophysicists get a crisp image of the things that they are seeing. Although refracting telescopes are simple to make, they actually have one condition that stops them to become effective, and that's called chromatic aberration. And this was an issue that a lot of astrophysicists have pondered upon in the past, but now we have resolved it with a new development of lenses and telescopes. And so chromatic aberration is that glass bends different wavelengths by different amounts. And so this is a material defect that's produced by the refraction of different wavelengths coming at slightly different angles. So maybe it would come here, here, here. There wouldn't be a focal point because it would be coming at different angles, hitting different spots. And so this causes the light or the images to be produced incorrectly, and it would be blurred. So how did astronomers and astrophysicists deal with this material defect problem? Well, they came up with something called the reflecting telescopes. And the reflecting telescopes differ from the refracting telescopes because they simply use a mirror to bring light to a focus instead of a lens. And so this was actually more effective. The first one that they used was a spherical mirror, like this. However, spherical mirrors actually give you something called spherical aberration. And this is the same thing as chromatic aberration, which ends up in a failure to focus. Astrophysicists aren't able to see the image clearly. So they came up with another solution, and that was using a paraboloid mirror. So usually you would see a parabola like this, a U-shaped, and this structure provided a solution for astrophysicists to solve this problem. I'm going to quickly illustrate this so you can get a better understanding. We have the light rays coming in here. This is the spherical one, and it actually ends up to be a bit farther away from the focal point. If we have a spherical, the light rays come in here and it diverges on top of this focal point. Spherical aberration and reflecting mirrors with the paraboloid. The last topic we're going to cover before we end the video are telescopes in space. I'm going to give you 3 reasons why having telescopes in space are better than having it on Earth. So the first reason is that there's no distortion. So telescopes in space. And by no distortion, I mean that you can see a better and clearer resolution, clarity, because there's no blurring by the Earth's atmosphere. And as you know, all the air molecules will blur your vision. The second reason is that you will have a darker sky. So by having a darker sky, you can see clearer in the infrared, and sometimes in other wavelengths as well. Third reason is that we can see UV, X-rays, gamma rays, and infrared radiation. So we're able to detect more wavelengths and more ways for us to examine patterns and planets and etc. So that's the end of the video. I hope you enjoyed. In the next video, we're going to talk about the twinkling of stars, blue and red sunsets, and the phases of the moon. Thank you.